Started. Welcome everybody. Are you here for hydrologic engineering? Good. That's what I'm here for. Yep. So I don't know if you're familiar, but this course is going to be undergoing a pretty radical revision compared to how it's been taught before. And the reason why is that we wanted to make the course more design oriented. So I think some of you are taking it this semester as a civil engineering design elective, right? You are. In the past, it was just taught as a civil engineering elective, which meant that it wouldn't satisfy some of the degree requirements that it will this semester. And so to make that feasible, I had to rearrange some of the content to later in the semester that ordinarily I would start at the beginning. So all of that's just to tell you, it may take me a couple of days before I'm able to get the lecture notes posted online, but I do plan to do it. I'm just kind of trying to figure out how it's all going to fit together. It's a little bit of a jigsaw puzzle at the moment. But there are going to be two separate design projects in the class, as we'll talk about here in a minute when we look at the syllabus. In fact, let's just do that right now. We'll start with the syllabus. I handed it out. Does everybody have a copy? Anybody need one? Okay. Similar to if you were in hydraulic engineering today, I mentioned that there were a handful of students who were taking that class as a graduate student, and the same thing is true in here. It's a cross-listed course where most of the lectures are in common between the two classes, but the graduate students are going to have additional readings, additional assignments, and projects that the undergraduate students don't. So this is the syllabus that applies to hydrologic engineering, but I'll prepare a separate graduate syllabus and schedule that I'll give to those students later this week. The prerequisite is just fluid mechanics, and although it would maybe be better if you'd also taken hydraulic engineering before this, it's not required, and especially the way that the course is being redesigned this semester, where I'm going to be pushing things like the design of culverts to the end of the semester. I think that it will be totally fine for those of you who are taking both hydraulics and hydrology in the same semester. So we're going to meet Monday, Wednesday, Friday at 1, and my office hours are Monday and Wednesday from 2 to 5. The syllabus has details about how you can get in touch with me, including email and phone, and if you want to call me on Teams, that can be useful. We're going to use a couple of software packages in this class. One of them is called Watershed Modeling System, which is put out by a company called Aquaveo. And then the other software that we're going to use is HY8, which is a product of the federal government. I don't remember exactly whether I think it's the Federal Highways Administration, but yeah, I think it's the Federal Highways Administration that puts that out. It's free. Both of those software packages, though, are only available for Windows. They don't have Mac compatible versions, and so if you don't have a Windows laptop, then you'll need to get a hold of one for a lot of our class meetings when we're going to be using that software in the second half of the semester. Our textbook is Water Resources Engineering by Larry Mays. Does anybody already have a copy of it? Yeah. I didn't look to see how much they're charging for it online. Let's just do a quick search because that's always interesting. Water Resources Engineering, Larry Mays. Amazon's usually a good starting point. Well, I like the $8.52. That sounds pretty good, but the paperback version, which is the one that I have, is $60. I don't know. Somebody acts quickly. It looks like maybe on the secondary marketplace there's some cheap ones available. $8.52. Snap it up before somebody else does. The book is important because I'm going to give you a list of terms, like vocabulary terms, that you'll need to familiarize yourself over the course of the semester. And some of them are terms which I'll use in the lecture, and others of them are terms that you'll only learn if you have the book. So you'll need to follow along in the book And at the very least, you're going to have to go into the book to maybe make a set of flashcards for yourself to learn this pool of vocabulary that anybody coming out of a hydrology course should be familiar with all of this lingo. So I'm going to post that online, and I may even give you a printed copy just to drive home the point that I'd like you to learn that language and be ready to answer questions to that effect on our exams. So the book's important for that reason. And, one person's explanation on a concept is oftentimes not going to be enough to really understand it and also to retain it. So I'll do my best, for example, to explain different types of precipitation, but we only have 50 minutes for our class lecture, and some topics are just much bigger than the time that's allotted. So you can't be expected to master hydrology or really even be well acquainted with it unless you put the time in reading the book. So I think it's a worthwhile investment, our textbook. I've already mentioned the issue with the no Mac version of WMS or HY8, so you'll need to have access to a Windows compatible laptop during the classes. And that's because we're going to do some in-class activities together where you'll need to have the computer here in the classroom, and also in the exams I'll give you some problems that you'll solve using the computer. Here's the list of outcomes for the course, the things I want you to learn over the course of the semester and how it's practiced and how it's assessed. The due dates and requirements on a topic-by-topic level or at the end of the document where there's a schedule. But there's a variety of policies here that are important. I'll just sort of breeze through these pretty quickly. Attendance is expected, but I'm not going to be taking attendance, and it's not part of your course grade. So if you miss class, my recommendation is to catch up on the material that you've missed by going through the notes, talking to your classmate, reading the book, and reviewing the lecture that's posted online. Late work is not accepted. When there's a due date for an assignment, it needs to be submitted before the due date or not at all, unless you have a university excused absence, which you can request through Student Affairs. And so the link to request a university excused absence is on the syllabus. Academic integrity is something that you need to be careful about this semester, and I do acknowledge that there's benefits of collaborative learning. I think it's good if you have discussions with your classmates and you work together, but then you're going to be examined on an individual basis. In this class, on the FE, when you go to your first job, you'll be interviewed on an individual basis, and so it's not what a pool of people knows that's ultimately the most important thing in this class. It's what you yourself know. And I think that you'll develop the best level of individual strength if you go through the homework assignments on your own, with the asterisk that it's okay if you check your assignment answers with other people, and it's okay if you talk about the homework assignment in general terms with people, but you should avoid crossing that line into showing somebody every step of a problem or sitting down at a table together and working through it at the same time, because in a situation like that, the person who naturally works a little bit more quickly is going to be doing most of the mental work, and then the person who naturally would maybe be more deliberate is just going to mimic and follow the lead of the faster person. So I'd encourage you to read over the specifics of this policy and be cautious in that regard. And I'll just finish that part by mentioning that when you submit work, it's expected that it's your effort. It's not ChatGPT that wrote the paper. It's that you that wrote the paper. If you're submitting a homework assignment, it's expected that what you've written is a reflection of the mental process that you went through in solving the assignment. So if you cross over the line into inappropriate collaboration, then both the person who provided the inappropriate collaboration and the person who received it is going to receive penalties that's more severe than a 0 on the assignment, quiz, or exam in question. So those and other university policies are available on the Academic Affairs website, which you can get to with this link. If we look at the grade breakdown for the course, you'll see that 20% of the grade is from assignments, 20% each for the 2 midterm exams, 20% for the final exam, and then we have 2 design projects, each of which are 10% of the course grade. And then when it comes to calculating your average score for the homework assignments, I'll drop the one lowest assignment in the semester, whether that's an assignment that you missed because you were busy with other things or forgot, or if it's the just the lowest score of all the ones that you did submit, that'll be dropped. So here's the schedule that shows which topics we're going to be covering on what days and when you can expect homework assignments. So you'll see that the first homework assignment is due on Wednesday the 17th. Then the following one after that is due on Monday the 22nd, and so on through the rest of the semester. The graduate students in the course have a research project report that's due on February 12th, and then this column also has when each of the design projects need to be submitted. And at the end of the semester, we actually have the last final exam slot on the last day. So Friday afternoon, we're going to be here to the very bitter end. And then many of you have graduation that very next day. So we'll see about that. I'm sure everybody will do great. Any questions on the syllabus or schedule? No? Well, if anything pops up, you can send me an email or stop by. This shows like what you're supposed to be reading as well in the book. So, ironically, both hydraulics and hydrology, we start in chapter 7. I don't know, there's something magical about 7, but that's where we start. Okay. Well, anybody recognize this place? Let me dim the lights a little bit. It's Lake Huntington. Yeah, I took this photo from my car a couple of years ago. I don't remember exactly when. I guess I could look at the time stamp of the picture. I should put the date on here. But, I mean, this is just an illustration that hydrology is an issue which affects the area, right? Somebody who had a medical emergency on this day is going to have a tricky time getting to the hospital, regardless of where they are, especially because between us and the hospital, you got to go under the railroad tracks, right? Is that true? Like, Hal Greer, does it go under the railroad tracks? I hardly ever come on a Hal Greer. I know most of the other ones do. Yeah, so, I mean, those are notoriously flooded. Like, it doesn't take a lot of rain before the railroad tracks are in trouble. I mean, usually by the time it gets to this, you'd need like a scuba mask to get to the other side of the road. In fact, this has happened several times where all of the underpasses under the tracks are totally flooded, and then 3rd Avenue gets totally flooded. So for me to get home, which is out in the area of Ona, like past the mall, I have to go all the way down to West Huntington. And so if you go to West Huntington, you can get up onto I-64 without having to go underneath the railroad track. So that's a secret. Next time we've got a flood like this, drive to West Huntington and you're golden. But this happened on a day where there was just an intense rainstorm. It wasn't necessarily the amount of water, but just how quickly that it fell that caused this flooding. And it had also been a little bit rainy in the days prior to this, just enough that the soil was already pretty well saturated. And it affected something which is called the antecedent moisture condition, which is how saturated the soils are in the period prior to a storm event that we're interested in. So we know that flooding can be an issue in Huntington. We're going to talk about all of the reasons why that is. We're going to start this semester by just talking about what is this stuff that falls from the sky and where is it coming from, like precipitation. Why does it occur? And we'll, at the end of the semester, be looking at how do we get rid of all this water? Like, why is it that Huntington has this flooding problem? Why wasn't it anticipated in the future? This is urban hydrology, which we'll do a little bit of. I'd say the course, a lot of the fundamental concepts of the course apply both to urban and rural hydrology. But we'll have more emphasis on rural hydrology in this course than a lot of other schools might, simply because, Marshall should be focusing on the area in which it is, and a lot of the roads in our state are in rural areas, and a lot of the people live in rural areas. And so I want you to be well familiar with the tools that you could use to grapple with hydrology problems outside of urban areas. And so this is a picture of a watershed near where I live. You can see it's very steep slopes. But the interesting thing about this is where all of the water would accumulate to. You can see here's here's a stream, and this is just a lightly rainy day. But you notice that the water is it enters a pipe here, which you can't really see the pipe. This person is very meticulous. Usually, I'm surprised to see this many leaves because they're normally very, very careful about keeping the area clear of leaves and debris, because if this culvert, which goes underneath the house, becomes flooded, then the water from the watershed goes right up against the house, and it's going to start to scour and erode the foundation, flow alongside the foundation of this outbuilding. So there's a lot of people in West Virginia who build homes in areas that are subject to flooding only on a periodic basis. And so we're going to learn about ephemeral streams and the flooding that can occur there and the risk of flood damage when people are, they know that it's going to flood in a low-lying area next to a creek, but this isn't a low-lying area. Like, the main creek is on the other side of the road, and it's probably 15 feet below the grade of this home. This is just an issue of flooding due to proximity to water coming out of the watershed. So I want to give you kind of a roadmap of the concepts that we're going to address this semester, and like, what are the big questions? What are the big ideas? Like, what are we up to in a surface hydrology course? And by the way, I'll emphasize that this is mostly a surface hydrology course. There's also subsurface hydrology, which we'll spend probably 3 class periods talking about subsurface hydrology, which is the movement of water underground. We're going to be talking mostly about the movement of water above ground. So the big questions: if we have an area of interest, what are the runoff characteristics? So the area of interest could be a parking lot. If you think about the cars that are in the parking lot behind this building, what do we have to do to make sure that those cars aren't going to be submerged if it starts to rain? We have to maybe put some slope to the parking lot. And at the low point of the parking lot, we need to have inlets. And we have to make sure that the inlets have enough area to them that they can accept all of the water that's going to be coming over the surface. And we need a pipe from that inlet to take the stormwater somewhere that it has enough capacity to accept and receive the stormwater. And the pipe has to have enough slope that it will carry all of the water that's going to be generated during some design event. Now, how big of a design event? Do we want the parking lot to be robust enough that it's not going to have any puddles or flooding during a 1,000-year storm? We could, but that would be really expensive. So we have to sometimes in this study of hydrology ask ourselves, how often is it okay if the system fails? Is it okay if Hal Greer has some standing water for 15 minutes every 50 years? It seems like that'd probably be all right. If it's 15 minutes is all the water accumulation, but some facilities can't handle 15 minutes in 50 years. An airport runway is designed to really high standards when it comes to trying to avoid standing water at all costs. And so we'll look at different types of roads and how there's a differing threshold for what's acceptable failure. So for an area, whether it's a parking lot or whether it's some watershed that is running adjacent to a home. So if we have some area, what are the runoff characteristics? And runoff characteristics, that means how quickly does the water arrive after it starts raining? Like what's the delay? Or how much water is there in terms of like cubic feet per second? How much water is there for a certain size storm? And you know, storms, talking about the size of a storm, there's different ways we can talk about a storm size. Like you've probably watched the news before and they say, well, there was 0.8 of an inch of rain yesterday. So we can talk about storm in terms of a depth, or we can talk about storms in a statistical sense. Like we can talk about how big a storm is in terms of the probability that that storm would happen in a 1-year period. So there could be a certain storm that it's so big that there's only a 2% chance that it will happen this year. So it could be probabilistic. Or an annual recurrence interval is the inverse of probability. Like a storm that's so big it's only going to happen on a 2% probability this year. Some people would call that a 50-year storm, which doesn't mean it lasts for 50 years. And it doesn't even mean that it's going to be exactly 50 years till the next one comes. It just means that on average, it's a storm so big that it would be observed statistically once every 50 years. So there's a lot of different pieces to this idea of runoff characteristics. We could be looking at the rainfall component of this area of interest and how rainfall affects the runoff, because there won't be runoff unless there's rainfall. Runoff is some portion of the rainfall is causing the runoff. And so when we get into the details of rainfall, we'll be talking about the return period, temporal distribution. You're going to get 2 $5 words today. Temporal distribution is a $5 word that, like when you go home and talk to your parents tonight and they say, oh, how was the first day of school? Say, well, we learned about temporal distribution. And they'll say, wow, he's really getting his money's worth over at Marshall. They'll just think you're getting a heck of an education, and they'll go nuts if you talk about spatial distribution. So temporal distribution is how does something vary over time? So in Seattle, when it rains, it's just kind of a constant mist all day long. It's a linear distribution of rainfall over time. Like if there's 1 inch of rain in a day in Seattle, the rate is pretty much constant through the day. That's just the type of storms that they get in Seattle. But here in the Midwest, it's a type 2 temporal distribution, and what's typical for a type 2 temporal distribution for precipitation is the rainfall sprinkles a little bit, and then it rains really, really hard, and the majority of the depth occurs over a very short time period, and then it keeps raining for a little while after that. So there's just kind of an all-at-once intensity, and we'll talk about why that is, but that's temporal distribution. And now spatial distribution is discussing how patterns are varying from one place to another. So it may rain really heavily at the Huntington Airport during a certain storm, but it could be really light here in town. Or on the windward side of a mountain range, so that's the side of the mountain range that the wind is blowing at, it would be wet there and really dry on the leeward side of the mountain range, which is once the air goes up and over on the other side of the mountain, sometimes it can be a desert, whereas the windward side could be really lush and green. We'll look at some maps of Hawaii, which is a really dramatic place that you can observe spatial distribution of rainfall. We're going to talk about infiltration, which is the capacity of soil to absorb water. So the capacity of the ground to take water depends on 2 main things: the type of soil that is in a location and the land use. Land use being, is it a parking lot or is it a forest? Because as you'd expect, if you've got a parking lot, then the amount of infiltration is going to be limited. It's like you've got this layer, an impervious surface on top of the soil that prevents infiltration. Whereas if you've got, well, this picture from the first photo, if you've got this is going to soak up water like crazy. there's not going to be a lot of runoff in an area like this because these ferns, this nice loose soil, all of the forest litter from years and years of falling pine needles and leaves and so on, that's just going to hold on to the water, and especially because this appears to be relatively flat, we wouldn't expect to see much runoff compared to a parking lot. So that's the difference between, where are we? Land use and soil type from one place to another. Antecedent moisture, that's a phrase I've already used today, just talking about how rainy was it in previous days. Do you have soil that's parched and baked and dry after a period of dry weather and drought? Because it could be very thirsty soil, so to speak, with a really high suction pressure, or it could be already saturated, and then when rainfall occurs over saturated soil, there's going to be a lot less infiltration and a lot more runoff. Abstractions are things that reduce the amount of water that's going to run off. And so if water is puddling on a leaf and is evaporating into the air, then some of the water from that leaf may drip down onto the ground and contribute to runoff, but the portion of the moisture that evaporates before the rain hits the ground isn't going to contribute to the runoff. Interception is the effect of buildings or trees which absorb some of the precipitation before it gets to the ground. Have any of you noticed that some of the trees in Buzzkirk Field have like a weird wrap around it, and then there's a cylindrical rain gauge? You'll see it if you walk over there. They're trying to measure how the different types of trees absorb rain. And I've done some similar research out in the field looking at during the summer when all the leaves are on the trees. You probably stood under a tree on a rainy day, right? For the first few minutes of a storm, it can keep you pretty dry. After a while, not so much. But that's what interception is. There's things between the clouds and the ground that absorb some of the rainfall. And surface wetting is that there's some quantity of water that has to get the ground wet before flow can occur over it. So a parking lot isn't going to just, the first drop of water that hits a parking lot isn't going to start moving laterally. You have to coat all of the pores of the asphalt or the concrete, and then additional layers of moisture on top of that will then be able to move over the surface after the surface has become wet. So a certain quantity of water is bound to the solid above it. This semester we're going to use some software to do watershed modeling, but behind the software are equations that we'll also solve manually that quantify how much of the rainfall goes to infiltration, how much of it's satisfying abstractions, and then how much is left over for runoff. So runoff characteristics is when it rains, how much of that rain is going to be moving out of the watershed, and the hydrograph tells us what sort of a time course that takes. You know, is it going to be really quick after it starts to rain? Is there going to be a lot of water all at once, or is it going to be a long drawn-out period that the watershed is draining? And there's different factors that can contribute to the shape of the hydrograph. And routing is talking about the travel time. When water gets into a stream, there's a delay of, if water enters the Ohio River here in Huntington, that water takes some time to make its way towards Mississippi. It's a couple of days when there's a big storm in the Midwest before they really notice a flood of water at the outlet of a watershed. So we'll look at some ways to calculate the routing time that water takes as it travels through a network. So this is kind of the overview of what we're going to do this semester in terms of the science. And this class is really polar. It's a lot of science and a lot of design. And so the science part of it maybe is going to feel weird to you, because for most of you, it's probably been a while since you took a science class. You had physics and chemistry, but that was largely during your freshman and sophomore years, and maybe you haven't taken any science classes. So it's going to feel weird to make flashcards and memorize vocabulary, but I mean, it's important to know the science to be able to do the engineering. So the implications, once we understand these forces that dictate the amount of water that's running off, then they allow us to do things like size culverts that go under roads, to understand how large inlets should be for storm sewers, and trying to reduce the risk of flooding through floodplain management. Any questions so far about what is surface hydrology? Okay, so here's our announcement slide. Homework number 1, the precipitation assignment is going to be due on Wednesday the 17th. I don't have that posted on Blackboard yet, but I'll post it today before the end of the day. And so that'll be due on Wednesday. That's the only thing that you really need to have on your to-do list, other than getting a copy of the textbook as soon as possible. So here's some more pictures of weather gone wrong in West Virginia, flooding. There's a lot of flooding that happens across the state, and it causes property damage. It causes secondary effects, like businesses that otherwise would move in and help to develop the area's economy are sometimes reluctant to do so if they know that there's this uncertain risk of experiencing flooding. So it's not just people having to shovel mud out of their front room, but it's also the fact that companies are less likely to invest in areas that are flood prone. The cost of flood insurance can really drag people down. It can be a big part of some people's budget if, unfortunately, a lot of the flat ground that we have in West Virginia is very close to a stream. It's either you're next to the stream or there's hilltops, and it can be really expensive to build on the hilltop because you've got to do all the earthwork from the road to your home. So most people choose to build their house close to the stream, and then they're threatened from flooding. So I think we all can recognize that in a wet climate like we have here in West Virginia, hydrology is important. I think on average we have around 40 inches of rain per year here in West Virginia. And so hydrology is important in wet climates. Here's a picture of Richwood, West Virginia. And one of my, let's see if this video is still online. I think they may have taken the link down. Oh, here it is. Anybody seen this video before? Have you seen this clip? It's a burning mobile home going down the river. It's like double destruction, I guess. This was taken during the storms that happened in 2016. Yeah, pretty sad. Bad day for those folks. FEMA doesn't really give you a lot of support when there's an emergency. There sometimes will be like additional grants that are put on top of what FEMA does provide, but there was some flooding in Kentucky maybe a year and a half ago, and the people who were affected there just got a couple $100 in FEMA support, and a lot of them didn't have flood insurance. So hydrology is important in wet climates. It's also important in really arid regions, and I know a lot of you are in 331, and I already mentioned that I used to live over in a very dry climate. In contrast to the 40 inches of rain per year that we get here in West Virginia, over in the United Arab Emirates, they get 4 inches of rain per year, so like a tenth of the precipitation that we get. It's important though because they have really rocky mountains, and there's flashy streams that'll form coming out of the mountains. They have more or less used up all of the groundwater in the United Arab Emirates, and now they rely on desalination, which is really expensive. Desalination, to produce a cubic meter of drinking water through desalination costs like directionally about $1, whereas water that we get from the Ohio River costs about a penny per cubic meter. So, I mean, it makes your water 100 times more expensive if you're having to resort to desalination. Now, because of that, they've gone to great lengths in the UAE to try and construct groundwater recharge dams, to try and bring the groundwater levels back up. So even though they only get 4 inches of rain per year, they don't want it just to evaporate. They've gone to some great lengths in building reservoirs they exist mainly so that the water will percolate and infiltrate back down underground and fill the aquifers that have been previously deleted. So these are 2 different dams. This is an area that I used to go out to just for runs on the weekend, and I happened to be out there one weekend after it rained and got a picture of this puddle before it evaporated and went down into the ground. Here's a look at what happens in Dubai when it rains. They don't have a lot of storm drains there. Similar problem to us. We don't have big enough storm drains in Huntington for different reasons. In Huntington, we have a combined sewer at a lot of places, which is both wastewater and stormwater going into the same pipe. And so part of the reason why we have so much flooding is that the pipe's already largely full from wastewater, and then a lot of the pipes were put in the ground before Huntington was built out, and sometimes before Huntington was paved or before the invention of the car. Like, they didn't have in mind that there'd be so much asphalt and parking lots and so much roof area. So there was less infiltration or less impervious surfaces when Huntington put pipes in the ground. And over here in the UAE, they just don't think to put in storm sewers because it rains so rarely, but then people end up parking in a low-lying parking lot that's just sand, and it becomes saturated sand, which then causes a lot of economic damage to the vehicles that are parked there. So hydrology is important in wet areas as well as in dry areas. For a lot of years, the UAE would react to flooded highway intersections by sending these trucks out there to like suck the water out. And that's, you drive on a rainy day and see all these trucks out, like vacuum trucks, similar to like how septic tanks sometimes get vacuumed out by trucks like this. There'd just be truck after truck lined up to vacuum the water out of these flooded intersections. And in a hot area, it can be a problem because these puddles will be a breeding ground for mosquitoes. And so it can last for days if the sand is saturated and it's pretty humid over there, so the water doesn't evaporate as quickly as it would if it was low humidity. This is some pictures from the campus that I used to work at, and they didn't have any kind of storm inlet drains on campus, and so when it rained, just the low end of the roads would be completely flooded, and you'd have to just find an alternate route or stay home. Most people just stay home when it rains. It kind of causes paralysis. This is the academic building that I used to work in here on this side, and they had all this polished granite and marble for the walkways rather than concrete. They have like marble and granite, and it's really slippery. So on a rainy day, you have to be pretty cautious about not slipping because it's awfully dangerous over there. The relationship between hydrology and hydraulic engineering is that hydrology comes before hydraulic engineering in providing the information that a hydraulic engineer needs to size a pipe. So a lot of you are taking both classes this semester, and hydrology tells you when it rains how much flow there is. And so you're taking a storm event and getting Q, where Q is the variable that we use to describe a flow rate. And then the hydraulic engineer takes the information provided and generated by a hydrologist and says, if there's a certain flow rate, how big should the pipe be to accommodate that flow? So there's a continuum. People who work in hydrology often do hydraulic engineering calculations, and hydraulic engineers oftentimes are able to do hydrology analysis. It's not always two separate people. But what I wanted to point out with this slide is just that the information that comes out of a hydrologic analysis feeds into the hydraulic engineering that gets done. So hydrology is studying the amount and distribution of rain at the surface and the runoff that occurs from that. And it feeds into both the open channel flow and the pipe flow aspects that are a part of hydraulic engineering. Okay, water moves about in the environment driven by the sun. It is the sun's rays that provides the energy to evaporate water from the ocean. And then when moisture has evaporated, then it condenses onto dust and salt particles in the atmosphere. And then when conditions are right and the cloud is fully saturated with moisture and becomes the water droplets become heavy and they collide with other water droplets, then the moisture will fall downward either as rain or snow or sometimes as hail and sleet. The precipitation can fall either back onto the water, or the water can fall onto things like onto the surface, and it could either run off or infiltrate down into the soil. Water can fall directly onto streams, in which case it just generally ends back up out at the ocean, or if it collects in a lake, there can be additional evaporation that occurs from freshwater lakes. But this water cycle is circular, and I mean, you can definitely waste fresh water, but you can't necessarily waste water itself because, you know, we're in an enclosed loop. So there have been a variety of efforts recently to take seawater and desalinate it and inject it into groundwater to prevent further saltwater intrusion. And we'll talk about that principle, the idea of saltwater intrusion, through the semester. But the amount of water that is at any given stage here is characterized in this diagram. This is kind of saying for every 100 units of precipitation that happens over the Earth's surface. So this is on a global basis. This isn't talking about one particular spot. That's not like this isn't Seattle or Hawaii or something. This is like a global average, is that if there's 100 units of rainfall onto the Earth's surface, the land, then there's going to be 385 units of precipitation where it's rainfall that just goes right back to the ocean. And that's because more of the Earth's surface is covered by water than is covered by land. So between the two, that means that there must have been 424 units of evaporation from the ocean when we take into account that there's also evaporation from plants, from inland waters, and from soil itself. And so this just kind of puts some quantitative spin on understanding the water cycle. And so some of the water that gets into the ocean is seepage from groundwater that goes directly into the ocean. You can see some of the water that gets into the ocean is surface flow. So it's fresh water that has been rain in the past that's making its way back into the ocean. So this is showing an impervious layer that breaks subsurface flow into a confined aquifer, which is beneath the impervious layer, and an unconfined aquifer, which is above it. And when we get to the subsurface part of the course, we'll talk about confined and unconfined aquifers and some equations that allow us to calculate how much water can you actually draw from the earth when you have an operating well, and what are the forces that allow the water to move towards a well when you start to extract from it. Most of the water on Earth is seawater. Most of the Earth's water is found in the oceans. 96.5% of the global water is in the ocean. and a very small fraction of it is fresh water. The 2.5% of the water that's not saline, most of that is ice caps and glaciers, which we don't have ready access to that water. It's not the right place for us to use. It's at the North Pole, the South Pole, mountain glaciers that's really remote. So the same thing is partly true of groundwater. About half of the groundwater is so deep that it's not economical for us to pump it out. And so it's only the shallow groundwater, the relatively shallow groundwater that we have access to. But most of the fresh water that we rely on is this tiny little fraction of the available fresh water is surface water. You know, we get our water from the Ohio River. And so it's kind of miraculous if you think about how much we use and how regular that supply is when it's such a tiny fraction of the Earth's water, you know, that's fresh, and so little of the fresh water that is surface water. So it's kind of interesting to see that rivers is 0.46% of the surface water, and surface water is only 1.3% of fresh water, and fresh water is only 2.5% of the Earth's water. So we're really spoiled, the proximity that we have and the abundance of water being where we are, because there are a lot of people who don't have such ready access to water that doesn't need to be desalinated. This is the slide that we're going to leave things on today. This is the definition of a basin or a catchment or a watershed. And what I like to do to illustrate this point is bring up Google Earth Pro. So I'm going to show you when we get together in class on Wednesday by kind of like 3D pivoting around some watersheds in the area here, just how it is the high point of a ridge line that defines what is a drainage divide. So we'll get to that on Wednesday. In the meantime, if you want to get an early look at the homework assignment, it'll be posted later today along with that terminology that I suggest you begin familiarizing yourself with those terms. But the important thing is getting a hold of the book. So buy the book. See you on Wednesday.